maybe just right on time. So it's, as you know, this is going to be the last lecture of the series. It's going to be a continuation of the general kind of set of lessons I've wanted to convey thus far in at least the second half of my discussion, which is that amplitudes can not only help you relearn, like, basic facts that we know from QFT, but also illuminate genuine new structures. Okay, so let me share my screen here. Now, last time, where did we end off? We ended with this discussion of kind of curious unity between, let's see, let me back up here. Curious unity between amplitudes of all different types. Hopefully, I think you can see my screen here. So we had this kind of mantra that gravity is the mother of all theories. Do let me know if you can't see my screen. I think you can, but just in case, let me know. But the idea is that there are a couple of theories that kept showing up in scattering amplitudes. Of course, there's gravity, there's Yang-Mills theory, which are elements of the standard model. Similarly, the nonlinear sigma model, which describes pions, but then also kind of some other kind of strange bedfellows like Born-Infeld theory, special Galilean, and just kind of basic phi cubed. Okay, and what I want to talk about today is how not only can we start from gravity to get everything else, but how we can actually start at the bottom of this kind of tower like NLSM and Yang-Mills and actually work our way back up. Okay, so the upshot here is that there's going to be a huge number of connections between these. Now, before I do that, let me just mention as an aside, I'm not going to go through this, but the kind of amplitude statements that I showed here, all these kind of differential operators, they may seem very mysterious from an amplitudes point of view, but there's actually a kind of partial understanding of this in terms of dimensional reduction. Some of these mappings are kind of obvious. If you take gravity in higher dimensions and you dimensionally reduce, you can clearly get Yang-Mills. The kind of less intuitive fact is that if you could take Yang-Mills in higher dimensions, there's a way of compactifying it in a very peculiar way that actually gives pions. Okay, and similarly, you can go from gravity to Born-Infeld to these other theories. Okay, so in other words, I'm not going to go through this, but there's a kind of very concrete sense of compactification from higher D to lower D, which actually implements this at a more Lagrangian picture. Okay, now that all said, let me now move on to this lecture today, which is going to be on my kind of final and I think, in my view, the most interesting structure that exists and has been found in amplitudes, which is the so-called double copy. Okay, and I'm gonna show you. Well, we'll start from the 3-point function that we saw before. Okay, so this is the Yang-Mills 3-point function that we built from the bootstrap. Recall that the way we did this was we first built, the kind of unique function at lowest order in momenta, which satisfied this Ward identity constraint, and we learned that it was fully antisymmetric. Okay, and in order for that to be consistent with Bose symmetry, we introduced a structure constant that was also fully antisymmetric. Okay, so if you like, the kinematics in some sense was primary, and then this structure constant we added to make a consistent theory of a spin 1 boson. But the point here is that FABC, by construction, has exactly the same symmetry properties as this kinematic function. Okay? And by symmetry properties, I mean if you swap A and B, you get a minus sign. Here, if you swap 1 and 2, you get a minus sign. Okay, they're both fully antisymmetric and exactly the same. Okay, now, of course, this is a very nice mirrored structure. Okay, in other words, the kinematics and the color have exactly the same, if you like, combinatorial properties under swapping. Okay. Now at 3-point, you could ask if there's any significance to this, and it might seem, maybe this is some strange accident, but I want to argue and tell you today how this is actually, yes, there's deep significance that goes far beyond 3-point, far beyond Yang-Mills, far beyond even gravity. And I would argue in some cases, even beyond perturbation theory and even the flat space amplitude. Okay. And that's going to be what I'm going to unpack here. And the kind of thing I want to commit to is this notion that, since color and kinematics show up together in these circumstances in some kind of interchangeable way where you could kind of swap them, we can kind of embrace this duality, fully and just start swapping color with kinematics. Okay, so concretely, if you took this kinematic structure and just replace it with another copy of color, Okay, so this is a structure constant for a kind of barred color group. Then you get a new amplitude with no kinematics, which is, if you like, just a potential cubic term, which is why I'm calling it phi cube theory, except it has two colors, one color and a second color. Okay, which is why we call it BAS, which I mentioned last time is bi-adjoint scalar theory, because it's a scalar which is charged as an adjoint of one color and also an adjoint of a second color. Okay, so this object naturally arises if we replace kinematics with color. Now we can also do the opposite. We can take this color and we can just replace it with a second copy of the kinematics. Okay, now we also did that last time. We just take this thing and square it. And we saw that that wasn't just some random function, that was gravity. Okay, and this is the origin of the name double copy. Okay, the double copy refers to two copies of the kinematics of Yang-Mills yielding gravity. Okay, now hopefully you understand from 3-point that this should seem actually not so miraculous at low point. At 3 particles, we saw that this was a very small number of kind of gauge invariants we could write. It's not surprising that if we square it, we get the gauge invariant for a consistent theory, which turns out to be gravity. Okay, but as we're going to see, it's a much more general thing. Okay, so there's a number of other ways that this is kind of colloquially described. It's called gravity is gauge squared, also known as color kinematics duality, where just in terms of the name, the idea is that color and kinematics are on equal footing because this color and this kinematics have exactly the same kind of algebraic structure. So we envision that there's some kind of duality that links them and swaps them, called CK or color kinematics duality, which is it would be like another way of stating the same a squaring type property. Okay, now if this was all just a 3-point, this would be very much uninteresting. But in the seminal work of Byrne, Carrasco, and Johansson, BCJ, they showed that this generalizes to end particle scattering. Okay, for the moment, let me focus on tree level. Actually, for this whole talk, I'll focus on tree level, except the very end. And in fact, let me consider Yang-Mills theory. Okay, so let's just deconstruct precisely what the statement is. Okay, so let's take 4-point scattering in gauge theory in Yang-Mills. Okay, now in Yang-Mills theory, if you just wrote Feynman diagrams, you have these, factorization topologies, and then you have the quartic term. Okay, now of course you hopefully know from your Feynman rules that the 3 cubic diagrams with just cubic vertices you could arrange such that you have an S pole, a T pole, and a U pole, and then there's color factors C, S, C, T, C, U. And I'm going to define NS, NT, and NU as all the kinematic stuff. So we're going to call those kinematic numerators. It's everything that's not color and not the denominators. Okay, and here's the C's are just these usual structure constants, which we showed before have to satisfy the usual Jacobi identity by consistency, not as a sum from on high input, but from just consistency. Now, of course, I haven't told you what to do with the quartic. Okay, naively, it doesn't fit into either of these 3 bins. Okay, but of course, I can take a quartic and I can multiply by either S over S or T over T or U over U, and then associate it with one of these factors. Okay, so you can kind of jam it into here if I multiply by U and divide by U, or put it here, and so on and so forth. Okay, so the point here is I can take the quartic and also put it into one of these terms. Okay, so the whole point is that all of the Yang-Mills terms are kind of arranged in some way into these 3 pieces. Okay, obviously it's not unique the way you would do that, but choose any way you want. Okay, just make a choice. Okay, now what's the statement of color kinematics duality? Okay, well, of course, usual color statements just say this identity. This is just like a property of matrices, which is the color structures satisfy the Jacobi identity, and this is an identity. But here's a surprising fact. Okay, if you take NS, NT, and NU, okay, which I want to emphasize here, these are kinematic dependent. So these depend on polarizations and momenta. They also sum to 0. Okay, so I'm not going to do this for Yang-Mills, but I'll do this in some explicit examples in other theories shortly. But if we go on shell, so restrict to on shell kinematics, we find that the numerators in this theory satisfy precisely the same identities as color. This is not automatic. It shouldn't be obvious why this is true. And in fact, it crucially requires on-shell physics, but it is true. Okay, you can just check this yourself. And in fact, it doesn't matter how you arrange this term and distribute it, it will always be true. Okay, let me unpack that last statement a little bit more. Okay, this 4-point kinematic Jacobi identity, which is this thing, it holds for any gauge, choice, or field basis. Okay, so what do I mean by that? So let's say you chose to gauge fix in all kinds of crazy ways, like, or Lorentz gauge, or Gros Nouveau, whatever you like. Choose different field base gauge choices or field bases. Last time I showed you that you could even take the gauge field and you could write it in some totally nonlinear function, the gauge field, and that would give you a completely equivalent S matrix. In doing so, of course, A4 will be the same. That was the point. But the way the terms are binned into these pieces will change. Okay. And if you just do this exercise and change field basis, what you find is that the numerators change in the following very restricted way. Okay. NS, N, and NS, and T, and U will all shift by S, T, and U multiplied by some alpha, which could depend on kinematics in some crazy way, but it's the same alpha in all three channels. Okay. Now you can check this yourself just to see, but the reason that you can see why this was mandated is that if you change the numerators in this way, the Yang-Mills amplitude will shift, but in a way such that this S, T, and U cancel the poles, and you're left with alpha times the Jacobi identity, which is 0. So in other words, this had to happen so that the Yang-Mills amplitude was left invariant under field redefinitions. And it's easy to see that if you apply this to the Jacobi identity, so take this triplet, which started, let's say, something to 0, and you do this mapping, then you get a new term. But since S plus T plus U is also 0, then the kinematic Jacobi identity is satisfied no matter which basis you're in. Okay, but you can kind of already see the parallel here, which is that like color factors are canceling, kinematic factors are canceling. They show up in parallel, and that's why it's called color kinematics duality. Okay, so that's 4 point, which is again very simple still. But the kind of interesting insight is that at any endpoint, a similar statement is true. Okay, so let's go to 5 point. Okay, okay, you could just write down all the Feynman diagrams in the theory and then bin them according to cubic topologies. Okay, you can probably see that the kind of essential point here was you write everything in terms of cubic denominators that show up in the pure cubic theory. You take things that have quartics and you kind of associate them inside each of these bins. You can do the same thing at 5 point, where a diagram like this corresponds to some color factor, kinematic numerator, and denominator. Okay, so to be very concrete for this particular term, this color factor would be a product of structure constants. This denominator would be S12, S45, corresponding to this propagator and this propagator. Okay, and then the numerator is some complicated product of polarizations and momenta and so on. Okay, now what does CK duality say? So CK duality says, again, like the kind of generalization of what I just said before, which is that there is some representation of A5. Okay, this is in this case not generic. I can't go to any gauge choice and any field basis, but that there exists some way to write the amplitude such that the kinematic numerator satisfy the Jacobi identities. Okay, so you can see here that basically if I'm zooming into like a 4 point subdiagram in each of these cases, so it's less like just like the 4 point case, but I'm looking at a 4 point subdiagram, and in this case on shell, this is a three particle, this is a Jacobi identity for three states being swapped. And similarly, I can zoom into this set of 4 particles, okay, and this Jacobi is true. Okay, this again is a very non-trivial fact because these depend on momenta and polarizations. And the fact that this is true is rather miraculous that there exists any representation where this is true. Okay, now I say some representation because there's actually many representations where it is true, which is not a unique statement. There's many ways you can write the amplitude where this is true, but such a representation exists. Okay, and I'm going to call that a CK dual form. Okay, basically I'm saying there's a way of taking the amplitude A5 and writing its diagrams in terms of cubic topologies such that these identities are all true. Okay. As I said, it requires distributing the quartics in some way, which you have to be clever and smart about, but it exists. Okay, and the very non-trivial fact is that this CK dual form exists for any number of particles. Okay. Now, what is this bias? Okay, so you might think, okay, this is just some random curiosity. Okay, you could take kinematic factors and write them in a way that they exactly mirror the algebraic properties of the color structures that they come with. Okay, he's like, maybe that's just some weird fact, but here's where the real magic happens. Okay, which is the double copy. Okay, if I say that color and kinematics satisfy identical algebraic properties, why don't we just swap them? Let's really just treat them on equal footing. So I'll do exactly what I did previously, and I'll take, for instance, all the in this expression, here, take the numerator factors and just replace them with color. Okay, take NS, NT, and U and replace it with color. You can see very explicitly that you're going to get color squared, color squared, color squared. And this is the amplitude for bi-adjoint scalar theory. Okay, this is a cubic scalar theory where there's a S channel, T channel, U channel, and it has two colors. Okay, so this has two colors, no kinematics, because I threw out the kinematics and replaced it with color. Now, the vastly non-trivial statement, much more non-trivial than what I just said, is that if you do the opposite, take the color factors and replace them with two copies of kinematics, then you get the amplitudes in general relativity. Okay, that should be very surprising. Okay, so in other words, we took the color structures and just dropped them. We got the amplitudes in a theory without color. And in some sense, we doubled the kinematics. So we added more derivative couplings to the theory. And we find the extremely non-trivial fact that what we get is not just garbage, but it's the GR, Einstein's general relativity 4-point amplitude that we, well, I didn't compute last time, but you can also build from Feynman rules if you like. The reason why this is super non-trivial is that the NS, NT, and NU are not gauge invariant separately. You know, like NS, NT, and NU are like just like, you know, very complicated functions that change under gauge transformations. But somehow you can square them and put them here and you get a completely gauge invariant, or I should really say diff invariant amplitude, which is the one for GR. Now we can do even nuttier things, and this is where it gets even cooler. So I could take a numerator from one theory, which I'll call NS. I can take a numerator from a different theory. Okay, so you can imagine a Yang-Mills with a polarization called epsilon, and Yang-Mills with a polarization called epsilon tilde. And you can take their numerators and multiply them together like this and add them, and you get the amplitudes in an even bigger theory, which I call GR plus plus here, but that's just GR plus dilaton plus axion, okay? Which are, as I've mentioned before, the zero modes of the closed string. Okay, this should, I hopefully seem very miraculous to you. Okay, you're getting all the amplitudes in gravity plus dilaton plus 2 form by literally taking products and adding them. Okay, so all the hard work is in just, you know, if I just isolate where the hard work is, if you have spent, let's say, 40 years computing QCD amplitudes like the field has, you have them. All you need to do is arrange, you know, numerators in order to make this identity satisfied, the Jacobi identity. And when you do that, you get gravity for free. Okay, and that is at any number of n particle scattering. Okay, which is incredibly powerful, and that's a proven statement. Okay, that's not speculated with. It's been proven with BCFW, recursion, and all kinds of other tools. Okay, so that's the miracle. I mean, I would say small miracle, but I think it's pretty drastically remarkable. The statement is that lying within Einstein's general relativity theory that's over 100 years old is two copies of Yang-Mills inside it. Okay, now let me show you how this works in an example, and I want to kind of maybe rather than you know, distract you with epsilons and more complicated things, let me consider the simplest instance where it happens, which is not even gauge theory. Okay, so it turns out this double copy transcends gauge theory and gravity. One of the things I want to emphasize is that it's actually super general. It even happens in the theory of pions. Okay, the NLSM. Okay, so let me just show you a quick example. Let's consider a 4-particle pion scattering. Okay, now of course there's no color in the pion Lagrangian. Really, by color here I mean flavor. Okay, so for a G mod H coset, you can write flavor structures, which I'll call CS, CT, and CU. These are of course related to Riemann curvature of the internal field space, but I can write them in terms of CS, CT, and CU. Okay, satisfying the Jacobi identities from before. Which are just Bianchi identities of Riemann. And I can now study the NLSM amplitudes. Now, of course, you hopefully know that pion amplitudes don't have cubic interactions. I've said that many times. Scalars don't have intrinsic cubic derivative couplings. They go away. All you have is a single contact term. So you might worry, what do I mean by 1 on S, 1 on T, 1 on U? There's no cubic vertices in the pion action. Okay, but as I said, even though there's no cubic vertices, you have quartics. And the quartics you can rewrite in terms of these pieces. Okay. Now let me tell you what kind of the answer is. Okay. So I'm just going to give you what the expression is. If you choose NS, NT, and NU to be these formulas, S minus S squared minus U squared, U squared, then you can see manifestly that they sum to 0. Okay. So I've kind of hard coded the kinematic Jacobi identity. Now I just need to check that when I plug this in, I get the pion amplitudes that I expect from the chiral Lagrangian. Okay, let me just do that quickly. I mean, I won't even go through it, but the point is you just plug in those numerators, do some color algebra, and in the end of the day, you get S plus T, which is the well-known correct amplitude for the pion amplitudes. Okay? S plus T is the color flavor stripped pion amplitude of the chiral Lagrangian. This is correct. Okay, so this is like the example of what happens. You take, if you like, you could have started from here and you work your way backwards. Okay, but the point is, this is, these numerators correctly give pion amplitudes, but they are written in a form such that this is true. Okay, now once I have such a form, I can double copy to get amplitudes in a new theory. Okay, what is that theory? So let's say I take let's say I take the numerators, the colors that I have here, and I replace them with these numerator factors. So I just square the numerators effectively. Okay, you do that, you get this squared, this squared, this squared, and then you get minus STU, which turns out to be precisely the 4-particle amplitude for the special Galilean that we saw last time. Okay, so as I mentioned before, all the amplitudes that we encountered previously, we're going to find again and again and again. This is that higher derivative shift symmetry theory, and it is the double copy of pions. Okay, so just like gravity is the square of Yang-Mills, gravity is the square of gauge theory. The statement is that Galileans are the square of pions. Okay, and this is true at all number of particles scattered. Okay, same statement. Okay, so what we have here is essentially a multiplication table of double copies. Okay, you can take a gluon amplitude and a gluon amplitude for endpoint scattering, and in this very concrete prescribed way, square the numerators to get gravity. You can take pion amplitudes and you can strip off their flavor structures, okay, and take a product of their kinematics, and you get the amplitudes in Galilean theory. You can do even crazier things, like you can take a gluon amplitude and remove its color, throw away its color, take a pion amplitude and throw away its flavor, and then multiply the remaining kinematics, and you actually get the amplitudes of Born-Infeld theory. Okay, and this is at any number of particle scattering. Okay, these are all proven statements. This is not conjecture. This is a true statement for any tree-level scattering amplitude with any number of particles in all of these theories. Okay, it gives you a machine to build more complicated amplitudes from simpler ones. You use the machinery of collider physics from the last, as I said, several decades to just lift them directly to gravity to compute any gravitational amplitude you want at tree level. Okay, and what you have is essentially a multiplication table. Pion times pion is Galilean. Gluon times gluon is graviton. Gluon times pion is Born-Infeld photon. And then on top of this, we have bi-hadron scalar theory, which is like the identity matrix. Multiplied by anything, it gives the same thing. So if you do the same trick of bi-hadron scalar times anything, you get the same thing you started with. Okay, so it's really like a true multiplication table, but it's actual theories. Okay, the entire tree level S matrices of all these theories are mapped onto each other via this double copy procedure. Okay, now there's kind of two branches that I could describe of what this means. Okay, implications. One is just practical. Okay, the kind of litmus test for whether something's well understood is if it's so understood that you can make a better toaster out of it. And this is exactly kind of what's happened. Okay, this procedure of double copy is so well understood that we can make a better toaster, which is to say use it for practical applications, which I'm using a little bit loosely in terms of practical, but maybe I really do mean practical. Maybe semi-practically, it's been used for high order calculations in supergravity. Okay, so very high loop order calculations in supersymmetric gravitational theories are very hard to do with Feynman diagrams. But if you do them first in the gauge theory and then square them, then it's much easier. Okay? And this is of interest kind of from purely theoretical point of view, because there are these cancellations famously that happen in gravity. One amusing fact, which you may or may not know, is that, for instance, Einstein's general relativity, if you compute diagrams at one loop, it's finite. Okay, which should sound very confusing to you. Phi-4 theory isn't even finite at one loop. It has log divergences, but gravity is finite at one loop. Okay, of course, the two loop begets divergences, and with matter things are complicated. But there are these interesting calculations that are enforced in many cases by absence of counter terms. But there are even more mysterious ones that people have been trying to understand by doing calculations. Okay, that's kind of semi-practical because supergravity is kind of an idealization. More recently, and I think you team spoke about this, or maybe we'll speak about this, is that there's been a huge push now in amplitudes, applying all of our ideas to gravitational wave physics. Okay, and this used to be kind of a pipe dream of like, hey, we can get gravity from gauge squared. We should do this for LIGO, but it's become so concrete that it is now state of the art. Okay, so the kind of flagship state of the art calculations in what's called post-Minkowskian perturbation theory, which is essentially studying the binary black hole in spiral at order by order in G Newton. This state-of-the-art results are all from amplitudes. Okay, the first time they were computed, we're using scattering amplitudes methods. It's a great story that is dear to my heart, but I won't describe any of it here except in this one picture. It's a cool set of physics and even effective field theory. But I can tell you what basically we did, which is very simple. We studied black hole scattering amplitudes. Okay, you might say, what does that even mean? Well, in an effective field theory, a black hole is a point particle that has with couples to gravity. Okay, if you want to add tidal distortions, then you add higher dimension operators in that effective field theory that add non-minimal couplings. But ultimately, black holes are like point particles in an EFT, and you can compute their amplitudes, which would look like this kind of scattering where there's gravitons being exchanged. So we can compute this with our tools of double copy very efficiently. Okay, to very high order. You might wonder about loops because I'm saying classical physics, but and I can elaborate that, but let me just say that secretly loops include tons of classical physics, basically through phase-space integration, and we're using that to get classical dynamics. But of course, LIGO could not care less about black hole scattering, but we can use effective field theory matching to map this onto the Hamiltonian for a black hole binary and spiral. Okay, and that's in fact what we explicitly did, was we took the highest order calculation at the time of a 2-to-2 black hole scattering and used essentially NRQCD/HQET type methods to match that onto black hole binary Hamiltonian to get something which the people who build waveforms have folded into their comparisons against effective one-body numerical relativity and so on. So the people who do this are very interested and keep asking us to actually compute more things, so they care, evidently. And ultimately, for very high precision, it won't matter to have all the different widgets, numerical relativity, including analytics and their connection. So the upshot here is that, if you ever had a worry that amplitudes is about, n equals to 4 super-Yang Mills, extremely simple theories that don't describe the world, that is simply false. We have applied amplitudes to derive black hole binary dynamics and Einstein's general relativity beyond the order that it was ever computed by people who studied gravitational wave physics for decades before us. Okay, these methods have power and they can be ported to other fields. Okay, that's all I want to say about the kind of practical side of gravitational wave physics. It's a whole cute story, but let me move on to kind of beyond practical. Okay, which is the underlying structure of this multiplication table, which I think, if you just, know QFT, it should be very strange. I mean, like, why is gravity the square of gauge theory? Now, you might say, oh, this must be like Kaluza-Klein reduction, or maybe it's the fact that we have tetratic Palatini formalism, gravity is gauge theory. All those things are suggestive. No one's made the concrete connection. But this thing is really weird from any perspective. Pion squared equals Galilean. Okay, there's no kind of slick understanding, I think. Oh well, I'm going to tell you one, but this is not some obvious fact about the world. I think it deserves an explanation beyond just mathematically proving that these are true facts with amplitudes. Okay, and I want to now talk about kind of maybe general lessons you can learn from the double copy about QFT. Okay, so this is really the first place in this set of lectures where I'm going to not just tell you amplitudes facts that are relearning QFT facts, but I'm going to tell you new QFT facts that come from amplitudes. Okay, we're going on the reverse direction finally. Okay, and here's a very trivial fact. Okay, which is that the double copy has an immediate implication for Lagrangians. Okay, And this has to do with a kind of very simple observation. Okay, gravity can be written as a double copy. A double copy is given by a product of n and n. Now, both of these are Lorentz scalars. Okay, nt is our Lorentz scalar. So if I square, it's a square of a Lorentz scalar, which means that there's kind of a set of indices here that are contracted with one Lorentz invariance. There's a separate set of indices that are separately contracted, if you like, under a separate Lorentz invariance. Okay, I'm using Lorentz invariance, a little schematic here. This is my proxy for just the Lorentz indices here are contracted all with each other. The Lorentz indices here are contracted all with each other. Okay, what it tells you is that there's a way of writing gravity such that you can write every term so it has a factorized Lorentz invariance, where there's a set of Mandelstam invariants that contract with each other and a separate set, and they never mix. Okay, in other words, the amplitude has a hidden double Lorentz invariance. I should really call it a spin Lorentz symmetry because it acts on the indices, which implies, okay, at least a natural thing to ask is whether there exists a Lagrangian which manifests that symmetry. Okay, and I'll show you how you can derive it. Okay, actively derive it. Okay, so let's actually derive it. Okay, you could start with the Einstein-Hilbert Lagrangian. Okay, what's the Einstein-Hilbert Lagrangian? Well, it's just root minus gr, and there's a gauge fixing term. Now, as I said, there's a huge freedom and redundancy in QFT, which is field basis redundancy. The standard way people write graviton EFT is to just write eta plus h, just these first two terms. But as I said last time, I can add an infinite tower of nonlinearities, and none of these will change the dynamics. All scattering amplitudes will not depend on the free coefficients I dump in here. I add a whole infinite tower of stuff. Similarly, you can add a gauge fixing with arbitrary coefficients, and none of those gauge fixing parameters obviously affect any of the amplitudes either. Okay, now, so what I mean like super concretely is if you just literally plug in random alpha 1, alpha 2, beta 1, beta 2, any value of these parameters and compute 4, 5, 6 graviton scattering, these parameters drop out. Okay, I've even checked this personally just to see. It's kind of an amazing miracle. But of course, because we know about field redefinitions, it's totally unsurprising. Okay, so these by construction do not change the amplitudes. Now, they don't change the amplitudes, but of course they change the Lagrangian. Right? They very explicitly modify the Lagrangian. So you could ask, could I choose alpha 1, alpha 2, beta 1, beta 2 to make this property of doubled Lorentz invariance manifest? Okay, I'm not going to go through the exercise of that, but it turns out you can. Okay, so in other words, you can choose your Lagrangian coefficients here in a way where you still have Einstein gravity, but this is the action. Okay, I'm going to skip all the intermediate steps because it's kind of amusing, but it's amusing, but too much to talk about. But I'm saying that Einstein's general relativity at tree level can be written in the following way, where I define a sigma field, which is an exponential of a graviton field, and sigma inverse is e to the minus that graviton. So it really just means an exponential of a matrix, where that matrix is a 2D by 2D object with barred and unbarred indices. Okay, so I feel like I'm kind of like artificially labeling H with barred and unbarred indices, even though it's intrinsically symmetric. And I'm even writing derivatives with barred and unbarred indices. But in the end, I have one space-time. And my statement is when you just write this whole thing out, you get a Lagrangian for a graviton, and it's exactly equal to Einstein-Hilbert. And it has a C2, which swaps barred and unbarred indices, which means it has two separate Lorentz invariances. If you take any mu index and you rotate it, independently of the barred indices, you'll find two separate Lorentz invariances. Every single expression has a twofold Lorentz symmetry. Okay, now that's at the off-shell action level. Okay, so I mean, it's non-trivial to see why that is. This is actually closely related to so-called double field theory, but we've derived it using basically a combination of bootstrapping with field redefinitions and knowledge about what the amplitudes properties actually have to be. So this is kind of very baby version of like a thing you can learn. Okay, I don't think it is obvious if you know about general relativity that you can write it in a way that has two separate Lorentz invariances. Now, that's kind of telling you something about QFT, but I think a very noble goal, which I personally am still working on actively, is the following question: can you get the double copy from QFT? Is there a quantum field theoretic explanation for the double copy from first principles? Okay, gauge squared equals gravity is an interesting fact from amplitudes, but is it deep or is it just a curiosity? Okay, now how high are the stakes in this question? Okay, so let's just work through some hypotheticals. Okay, let's say gauge theory squared equals gravity is just totally not deep and is just a fact about flat space perturbative scattering amplitudes at tree level. Okay, at all in, but like it's just some random fact. Okay, that would be fine. A cool random fact. It goes nowhere. Okay, but let's say you find it compelling that it holds at all number of scattering, and then you could fold it into loops, and it's still true. Okay. Well, if it's true, I mean, it's been used, as I said, higher loop calculations. If you kind of conjecture that it's true at all loop orders, then it's natural to conjecture that it's true non-perturbatively. And if it's true non-perturbatively, it's very natural to conjecture that it's true in curved backgrounds because there's gravity. So let's say this is just an operation that's true non-perturbatively and in any background. Then this statement is insanely powerful because it means that you could take any question in gravity and turn it into a question about gauge theory, like in ADS-CFT. If there is a double copy notion that transcends scattering amplitudes, then there is a weak coupling duality between gravity and gauge theory, which would let you essentially ask any question about Alice and Bob in this language. Okay, now if you think that's too strong, it's totally reasonable to think that's too strong, then what that means is this must be a curiosity, and then we will fail to generalize any of this beyond flat space amplitudes. Okay, but if we keep finding more and more structure that lets us generalize this fact to curved space, to all loop orders, then we are approaching something very drastically, in my view, interesting, because it relates gravity to a non-gravitational theory. Now, why should you expect it to be a deep statement? And here I want to draw kind of an analogy, okay? The double copy procedure to the uninitiated or even the initiated should look very weird, right? It says, take the amplitudes, I mean, if I just go back up here, take the amplitudes at 4-point or 5-point and so on, and like reassociate coordinate terms in some funny way to make some structure apparent. I mean, it's just a weird operation, right? Like I even say like, take it and rewrite in a form. It seems very ill-defined, okay? But let me draw an analogy for what in my mind could be happening, maybe not, but might be happening, which is this kind of toy analogy, okay? Imagine you lived in a world where the universe was 5-4 theory, okay? We're a universe of 5-4 beings. But through some historical accident, we discovered the Lagrangian for 5-4 theory, not in terms of the phi basis, but in terms of some f of phi field, which was a Z2 violating function of phi. Okay, now from what I said in many lectures, this is of course physically equivalent to 5-4 theory. I just did a field redefinition. But the Lagrangian terms will all have many cubic and 5-point and 7-point interactions because f of phi was Z2 violating. So in this formalism, you'd have 6-point vertices and 5-point and cubic, and Z2 would be completely obscured. You would not see a Z2 symmetry in this theory. You'd have vertices that plainly violate the Z2. But when you add all of them up, the Z2 would cancel, right? These Z2 violating features are artifacts, okay? One way of saying that is that if you just rearranged kinematic numerators in some funny way, you'd find that you could rearrange all the numerators to preserve a Z2. Okay, so in other words, if you took this diagram and reassociated with this, you took this and reassociated with that by basically dividing by S and multiplying by S, you could always rewrite these diagrams in such a way that there is a Z2 preserved in every diagram, and that would be you re-deriving 5-4 theory in its canonical basis. Okay, so this idea of like manipulating diagrams and rewriting them is just a way of discovering structure in a Lagrangian which is yet to be understood. Okay, so this is my toy version of me trying to explain why I hope that color kinematics duality is this. I think that there should be a Lagrangian that has color kinematics duality as a symmetry, and we're just writing the amplitude in bad ways, and CK is just us rearranging it back into the good form. Okay, now this is not just an aspiration. I'm going to show you how to do this explicitly in a couple theories, and I'm going to give a field theoretic explanation for some of the double copies. Okay. So this is my question, not how do we use the double copy, but why does it exist? Okay, now if you ask this to many people in amplitudes or even any people in any context, many will be like, of course we understand why it's true. We calculated it and I could prove it as a mathematical statement. Okay, but I want to argue here that no one has any clue at all why the double copy is true. Anyone tells you they understand it, I want you to ask them this, okay? Does your argument apply off shell? Does it apply in curved spacetime? Does it apply non-perturbative? Okay. If anyone had a real answer to these questions, they would be able to answer you in 1 second whether any of these are true, and no one has any clue, right? You know, when we actually understand things, we know when they hold in these contexts. We understand things like anomaly cancellation and perturbation theory and current conservation. We understand it in all the contexts, off-shell, curved space. We understand how they apply in all these contexts. The double copy is something which we understand so poorly that we have no idea whether it applies in any of these contexts at all. So next time anyone tells you they have a proof of CK, I want you to ask them immediately, how does your proof generalize to curved space-time at all orders in coupling? And if they don't have an answer, they have no idea how to generalize the argument, which means they don't understand double copy. And I apply that to myself also. Now, I'm going to tell you now some understanding of double copy, which will precisely generalize to all these cases, okay? But not for gauge theory, for pions, okay? And this is a place where I think we made some real progress in actually giving a field theoretic understanding of this structure. Okay, it's not quite what I want, because I want to describe gravity and gauge theory, but there is a still miraculous and analytic statement, which is that pion amplitudes squared are Galileans. And I'm going to tell you why it's true in a way that transcends flat space scattering amplitudes. Okay, but let me do that. And as I said, I'm going to try to be as on amplitudes as possible because I want to give you a QFT explanation. So let's do some QFT. I'm going to derive a formulation of pions that manifestly has CK duality. Okay, let's start from what we know. Okay, this is the chiral Lagrangian, and I'm adding a source term for the pion. Okay, I can of course rewrite the kinetic term, or the interaction terms, in terms of the chiral current of the NLSM. Okay, so this thing is just J squared. Okay, J squared is of course famously conserved given the equation of motion for pions. Okay, so the chiral current is a conserved current. Okay, now of course the standard way to do pions is to just now choose U as e to the I pi. I set decay constant, pion decay constant to 1. But now you have an infinitude of choices. Okay, you could choose an exponential parameterization or a Cayley parameterization, as I think Mike Trott described or will describe. You know, in SMEFT, a similar kind of thing exists if you think of it in terms of geometric terms, which is there's really an infinite set of field bases, all of which are physically, you know, equivalent but look different, which you can make here. Depending on which choice you make, your couplings will look different. Okay, so you could pick this and then your couplings look some way. You pick this, they look different. But invariantly, no matter which choice you make, you have quartics, sextics, and a huge tower of pion vertices, which look very far from cubic. Okay, and cubic is important because we know that we need to organize everything in terms of cubic diagrams. Okay, hopefully that was clear from this discussion up here, which is that we want to organize things in terms of cubic topology. So we want a cubic action. And the pion amplitude is basically as far from cubic as you could possibly imagine. Okay, so naively, you know, we're in trouble. Well, what could we possibly do? Okay, now here's something, and again, I said the pion action tells you that the chiral current is conserved up to source terms, which produce pions at asymptotia. Okay, so we can build amplitudes ultimately. Okay, now here's going to be the trick. I'm going to tell you a formulation of pions which is completely agnostic of what field basis you're in. Okay, it's if you like going to be geometrically invariant and not care which pion embedding you chose. Here is the formulation. It's very elegant, and it's actually closely connected to a formulation by Friedman and Townsend from like 40 years ago, who never had thought about CK, of course, and they were using Lagrangians, but here's what it is. Okay, this is a first order formulation of pions. Okay, take the chiral current and think of it as your fundamental degree of freedom. Okay, if you like, forget that pions exist. Think about J as if it was the actual mode that I care about. Okay, and enforce the following condition. So this is the equation of motion for J. Okay, so let me enforce this as one condition. And now let me enforce also a second condition, which you'll notice is precisely the statement that the field strength for J is 0. Okay, this is just like in a Yang-Mills theory. This is like the field strength, but the gauge field is J. Okay, I'm basically saying it's a flat connection. Okay, now if you recall what this means from gauge theory, if J is a flat connection, then you can write it as pure gauge. Okay, which means that implicitly the solution to this equation is that J is this formula. So if you like, J equals this as an emergent solution to this equation. Okay, so if you like, U here has emerged. It's like been born from this implicit constraint. You could ask, how does U depend on the pion field? And I can say, I don't know and I don't care. It doesn't matter. I don't need to tell you because I'm going to deal just with J. But the point here is that this equation is enough to tell you that J contains an LSM field that has emerged from an implicit constraint, which is completely agnostic about what pi is. I don't care what it is, okay? Because I'm actually going to use J as my degree of freedom. Okay, so it's a little bit like, you know, constructing a theory not based on the field dynamical degrees of freedom, but instead based on a conserved current in the theory. Okay, now let me kind of push this to its logical conclusion. If you take this combination of equations, you'll get a wave equation for the chiral current. Okay, so this is not what, of course, we normally do, but this equation has a Feynman propagator. So this is an equation of motion. So if I interpret it as like a Behrens-Wheeler recursion relation, this is a Feynman propagator. This is the vertex. Now it has one J and a second J, which means it's a cubic interaction as precisely needed by color kinematics duality. And then the source term is like the original pion source, but it has a derivative. Okay, that's a one little interesting twist. Okay. But if you just handed someone this equation of motion, which by the way, looks just like the Navier-Stokes equations, just an aside, they would say, oh, that's cool. This is a vector theory with a cubic interaction. Okay. Of course, it secretly contains pions, but they don't know that. Okay, and you can solve for the S matrix corresponding to this degree of freedom. Okay, so that's what I want to do now. Let's extract amplitudes from this equation of motion. Now, of course, the first thing you should worry about is that, wait a minute, I don't care about current amplitudes. I care about pion amplitudes. I don't want the correlation functions of pions, of chiral current. I want correlation functions of pions. But here we can use a very amusing fact, well, not amusing, but just fact, which is that J is, of course, related to the pion. They're related by this connection up to ... which is field basis dependent. Okay, so in other words, I can write the pion as the chiral current plus corrections that are field basis dependent. Now you might wonder, oh no, this junk is going to come back to kill us and will depend on field basis. But as long as we compute on-shell quantities, all the stuff will go away. Okay, and in fact, that's precisely what we do. We compute the 1-point function for the chiral current. And by 1-point function, I just mean the solution to this equation of motion. Okay, so in other words, the equation of motion for J sourced by capital J, that defines the 1-point function for the chiral current, and it's exactly related to the 1-point function for pions. Okay, so I'll go through this a little fast because it's not super important, but the point here is that any pion amplitude can be related to chiral current amplitudes, so to speak. Okay, so in other words, the classical solutions to this equation of motion for little j encode all pion amplitudes inside them. Okay, if I just write down what the Feynman rules are for that theory, here they are. Okay, so here are the pion amplitude, here are the pion Feynman rules as you've never seen them. Okay, so notice there's no scalars, that should already bother you. There's no 4-point, 6-point, 8-point terms, they're all gone. The entire theory is a cubic interaction, a kind of Feynman propagator for a vector, and then weird external polarizations. Okay, but my statement is that if you just put all these diagrams together and just sum them up, you get exactly all pion amplitudes. Okay, these Feynman diagrams correctly reproduce all pion amplitudes. Now, you might be bothered by the higher spin objects, but the point is the polarizations get set to momenta in the end. So they almost look like longitudinal gauge bosons. There's a very close analogy here. Okay, it's almost like a massive gauge bosons in the decoupling limit. Okay. But the point here is that these Feynman rules give pions, and they give pions in the most bizarre possible way. Why is it bizarre? Well, everything you know about pions is obscured in these Lagrangian rules, right? So the pion Lagrangian, as you can see from the usual story, has, at least without a WZW term, has a Z2, G parity, right? Everything comes in an even interaction. So in fact, all odd point amplitudes vanish. Now these Feynman rules have a cubic interaction. So naively you have 3-point, 5-point, 7-point amplitudes, but on shell, they all vanish, okay? So if you like, the parity of the pion is obscured in this formulation. Okay, it turns out bow symmetry is also obscured, but in the end, despite obscuring all those properties, you still get precisely and exactly the right pi and amplitudes. This is a proven fact, and you can even explicitly check. I think we checked even up to 12-point scattering, just to be 100% sure. Now, it makes many things not manifest, as I said, but it makes one thing manifest, which is color kinematics duality. Okay. Now, how do you show that? Well, just take the Feynman rules and just compute this diagram, this cubic diagram, okay, and call the numerator n numerator the S-channel numerator. It's some kinematic function which you can just compute. And again, I'm not using any off-shell property. This is an off-shell Feynman rule. And you can do the same thing for NT and NU. And the surprising feature is that off-shell NS plus NT plus NU equals 0. Okay, these are off-shell Feynman rules where color kinematics duality is automatically manifested. Okay, so I'm saying the Cairo-Lagrangian has a form where every Feynman rule exhibits some kinematic Jacobi identity for kinematics. Okay, now why is that true? Okay, I've kind of established that this thing has CK. What's the field theoretic reason? Okay, and I'm going to tell you, it's actually very simple and elegant ultimately. There is a kinematic algebra. Okay, by this I mean, just like there's a color algebra, there's an algebra for kinematics. And the way it's related to color is that color algebras are sent to the diffeomorphism algebra. Okay, so what do I mean by this super explicitly? Imagine you have a theory with a colored object. So V is an adjoint of color, TA is a generator. If I want to apply the double copy to get pions, you literally take VA and replace it with a vector. You drop the color and replace it with a kinematic vector index. And you take TA and you replace it with a differential. Okay, so in other words, you replace this with the notion of a vector, like a vector in terms of the Lie bracket. Okay. The structure constant that you get from a commutator of color, colored matrices becomes the diff algebra's structure constant, which is literally this. Okay, so if you take this and another one and you commute them, you famously get the Lie bracket, which is just this commutator. And then the currents are mapped to this. Okay, so very explicitly, this kind of demystifies why color kinematics duality holds for pions. Basically, I'm saying take a theory that's not pions, take a theory with only colors, any theory, actually. So this is a general rule. Take any theory with a color index. It doesn't, in fact, I'll go through many examples. Take the color index and replace it with diffeomorphisms, and you will get a completely consistent new theory. Okay, why will it be consistent? Because the diff algebra satisfies all the same Jacobi identities as the color algebra. Everything will still hold. Everything that required Jacobi identity will still be true in this case. Okay, now let's just do that in examples. Okay, so let's take biadjoint scalar theory, whose equations of motion are this. I wrote this a number of times before, and the field is phi AA bar. Okay, now let me take the barred color and replace it with diffeomorphisms. Okay, so the regular color index is the same. That stays unchanged. Let me take phi and rename it J, but send A bar to mu. Okay, you can see that the equation of motion for a pure cubic scalar theory maps to an equation of motion for pions. Okay, this structure constant has become the diffeomorphism algebra structure constant. Okay, that's why nothing is surprising in the end. Every Jacobi identity that was satisfied by color is now satisfied by kinematics. Okay, so this explains how to directly get any pion expression from a phi cubed expression. Okay, now we can go even further. Okay, here's what you can do. You can do one level in again. Okay, so let's start with pions. Okay, start with the nonlinear sigma model, which I wrote in this form, and it still has a color, really a flavor index. Okay, I'm going to call it color flavor, and as I said, okay, let me take that color index and replace it with yet another Lorentz index. Okay, of course I'm going to call this J still, but basically take color, replace with Lorentz, take the structure constant and replace it with derivatives that are showing up. Okay, you get a new set of equations. This exactly defines a special Galilean. Okay, so this was a new set of equations we found that exactly reproduce all Galilean amplitudes. Okay, last but not least, let me take by far the weirdest case. Let me take Yang-Mills theory. Okay, Yang-Mills theory has color. Okay, Yang-Mills is defined by field strength and the field equation. Okay, these are just the standard Yang-Mills equations of motion. There's a gauge field and there's a field strength. hey, here's a color. Let me take that color and replace the color algebra of Yang-Mills with the diffeomorphism algebra. So A goes to mu bar. A here goes to mu bar. Okay, so like the field strength has become a 3-index object. The gauge field has become a 2-index object. And I have a crazy field strength that now has derivatives. Okay, this is secretly Born-Infeld theory. Okay, Yang-Mills, where color is diff, is Born-Infeld theory. Again, you can check just again, but by solving these equations of motion, they give you all the Born-Infeld amplitudes trivially. It's actually pretty remarkable. Okay, I'm gonna wrap up in 5 minutes, but let me just say something a little more about NLSM, which is that you can see here that this picture transcends flat space scattering amplitudes. Okay, just the notion color goes to diff. I can do that in curve space. I can do that at loop order. I can do that yada, yada, yada. And there's been a ton of progress in that direction. I'll get to that. Well, yeah, let me now tell you about that. And this is really kind of my final slide about double copy, which is that what I've shown you here is really, you know, I would say relatively modest progress in understanding the actual, what the kinematic algebra is, like why any of this is true. Okay, in terms of just writing an explicit Lagrangian, which really gives an explanation physically for why the color kinematics is existing. Here is some progress, non-exhaustive list of the progress. People have studied self-dual Yang-Mills in gravity, which is the all plus and all minus sectors. Unfortunately, those are trivial sectors where all amplitudes are 0, okay, which is a little confusing. But in that sector, people understand fully how to square, if you like, the amplitudes. Okay, it's a little sneaky because the amplitudes are vanishing, so I can unpack what that means precisely. But kind of the self-dual sectors of these theories at tree level, we can understand from double copy. Amusingly, 3D Chern-Simons theory at the Lagrangian level has double copy, and actually Henrik Johansson and friends showed this recently. All loop order, at any perturbative loop order, they can show double copy holds for Chern-Simons theory in 3D at Lagrangian level. What I just showed you just now in the last 20 minutes was how for pions, Born-Infeld, and special Galilean, equations of motion, which are tree level in general dimension, we now understand also. So it's not a Lagrangian, but it's, you know, the next best thing, which is an equation of motion, which gives us all tree level double copy. And I like it because it's got a physical thing I can tell you. What is the double copy for pions? Its color goes to diff. Now, very recently, even just this year, we managed to, actually literally this last year, since January, we managed to generalize statements we made above to very far beyond flat space. We generalized this double copy structure to ADS and de Sitter, and actually any maximally symmetric space. This is building on really great work by Radu Roybon and Aiden Hadershi and others, where they did in ADS. And the upshot is very interesting, okay? What does the double copy apply to? It applies to Witten diagrams or boundary correlators, okay? So if you look at boundary correlators and Witten diagrams, or equivalently in de Sitter space, coefficients of the wave function of the universe, if you Wick rotate, those objects manifest double copy. And it's exactly this statement, actually, except the diff algebra is given by the algebra of isometries of the underlying manifold. I could unpack that, but let me just move on. And then again, maybe even just in the last couple of months, we generalized an LSM double copy in 2 dimensions. Okay, so very low dimensional case, but we showed how you can do it to all loop orders and even for non-perturbative field configurations. Okay, so the video of this, I won't bother showing you, but it's the first ever, if you like, numerical solution. Okay, so what we did was we built a numerical solution in a theory, and then we showed how it's the double copy of another numerical solution for another theory in the large field limit, okay? Which means, you know, all orders in coupling, if you like, because we're actually evolving large field classical configurations. So that's a very explicit thing, which shows all loop orders and non-perturbative. Okay, that's all I want to say today in this set of lectures. I mean, hopefully I've been able to convey to you that there is, you know, there's been some partial progress. Let me actually stop sharing my screen and just talk. Hopefully I've been able to convince you there's been like some progress, well, tons of progress understanding, sorry, My video went out. Tons of progress understanding structure in amplitudes in and of themselves. Modest progress porting that structure back to QFT. And almost no progress porting it back to the very general context of beyond perturbation theory in curve space. And I think it's just, right in the beginning of trying to understand all these things. And if I were to give you, any takeaway message, is that like we're right in the middle of things. We are in no way towards the end of figuring out what's happening. Maybe in the end we'll discover it's all a curiosity that holds for, non-perturbatively in some special cases, but not generally. And I would be sad about that, but I still feel like I would have learned something about QFT. And for me, ultimately, I'm very unprincipled. I like the idea of using amplitudes as a tool for finding structure, but once you know the structure is there, if you like, you can just ignore amplitudes and just try to figure it out on your own. And I think it's an invitation to try to figure out what these structures mean, independent of any set of tools, which is kind of clearly what I was doing towards the end of these lectures. And I think there's going to be hopefully more progress in the coming years, and hopefully you could even be part of that discussion, and hopefully I conveyed the excitement that we all have in this community. And let me stop there and take questions. Thank you for your attention.
Are there any questions?
So thank you very much for very interesting talks. I have a couple of questions. First of all, you showed the field theory web, right? And can you have such a web for when you include the fermions in your And that's one question. And my second question is about your double copy. It seems to me that I don't know the superstring theory very well, but just I took the course a long time ago, and then it seems to me that the double copy may have a natural setting in the string theory, and gauge theory as an open string and the graviton as a closed string, making two open string, and you can make closed string from two open string, etc. Right? So is there any
Absolutely.
Yeah, so that's my two questions.
Great, thank you. Both excellent questions. So let me first tell you about the fermions. So for fermions, once you add them, of course, working with general dimensional fermions is like, complicated. You have to have, abstractly sized gamma matrices. The approach with fermions is you now fix a dimension. Oh, can you hear me okay? Did I cut out? For fermions, you would go to 4 dimensions and apply the bootstrap, and all the same ideas apply. I suspect that you team went through much of this. The bootstrap of just like what consistent fermions exist. You can learn about the gravitino as a consistent theory. I think that was even U-Team's paper with David McGady and others. The soft bootstrap story you can also do with fermions. So this is a very amusing story, which is that you can build the theory with nice soft behavior for a fermion. And of course, you might imagine what you're going to find for that theory. A Goldstone boson that's fermionic. What you discover is the Goldstino, right? So what you end up building is the VA, effective field theory for Goldstino coupled to other stuff. This was a very interesting set of papers by Henriette Elvang and others, where they add the fermion to the soft bootstrap. So you can build, the fermions are certainly a complication, but just the general principle of building out absolutely can be done and has been done with great effect. The second thing I'm also very glad you added, I just forgot to mention it. So the original double copy, the original squaring relation was the so-called KLT relations, which are descended from open string, closed string duality in string theory. These are tree-level relations which don't just hold for field theory, but if you like, hold for, including alpha prime corrections in full-on string theory. Extremely powerful relations. And they relate gauge squared as gravity. Okay. Now, there's multiple reasons why I don't think that's the explanation, just in my heart of hearts. I could totally be wrong, but here's why I don't think it's the explanation. So one just is the fact that the double copy that we're talking about here for BCJ, we recycle into loop orders, okay? So there's a kind of intrinsic sense in which we can get it to work at loop. While KLT was always a tree level statement, it was never understood beyond that context. Two, there are certain things that show up in the double copy that just seem impossible in string theory. Okay, for example, pion squared equals Galilean. You'd be like, okay, we'll explain this from some kind of really conventional string theory perspective. But there's kind of a weird hitch to that, which is, as maybe even Eutin may have described, the Galilean, all Galileans, special Galilean included, violates positivity bounds, positive dispersion relation bounds, because the p to the fourth coupling in the Lagrangian is forbidden by symmetry. And that has to be positive because of the forward cross section. Okay, so just for technical reasons, its symmetry is literally excluded and not consistent with any ultraviolet completion. So like it cannot arise from any kind of sensible string theory ever, right? It's just almost a fact. It violates axioms that we usually think of as precious to us. Okay, so that's one reason why I think it's something that should transcend string theory. But let me, even ignoring all those, just make a fact, a more sociological point, which is, I don't believe that field theoretic facts, things that are true in field theory, should require embedding into string theory to understand them. Okay, right? You could say, oh, how do you understand gauge anomaly cancellation? Oh, it's easy. Just go to string theory and you embed in a gut and then it happens. Like, how do you understand that anti-gravity doesn't exist? Oh, it's easy. Just go to string theory and you learn that you can't write it down. Like that's an argument, but it's a very poor one to understand the principles for why things are true. So let me be kind of an effective field theory QFT hardliner and say, if something is true in an effective field theory or QFT, it at least deserves an explanation that doesn't require me to introduce alpha prime, introduce Veneziano of your Zorship here, and then take the alpha prime goes to zero limit. It just needs its own internal explanation. So that's maybe, if you like, a hedge. I think there could totally be an explanation within string theory, but it would be kind of cheap to me if it was required. Like it would be weirdly like, I don't know, maybe string theorists would love it, but like personally, I would like field theory to explain its own puzzle on its own. But definitely there's an understanding. Maybe another technical point I make is that KLT doesn't give any signs of this kinematic algebra. Okay. The mechanics of KLT are not like the mechanics of double copy that I mentioned with BCJ, where you square numerators. This notion of Jacobi, that's all very foreign to KLT. And to me, I think it's the kinematic algebra, which is like the deep, interesting thing. It's a really cool new element, which I can explain to anyone. The kinematics of amplitudes obeys something analogous to the color kinematic identity. Why? Okay, and that question just doesn't show up in KLT, even though it's clearly related to the double copy. I mean, it's the same types of amplitudes and relations. Hopefully, that's kind of a long-winded answer, but hopefully I think it gets to what you're asking.
Thank you.
Yeah, any other questions?
I have a question about the kinematic corrective ns plus nt plus nu equals 0. So it is the empirical fact or it is proven rigorously for any theory? And if so, what is the critical point to prove it?
Excellent. So it's proven. In fact, there exists a formula for ns, nt, and nu such that is true. Okay, so this is kind of amusing. So the formula is actually very simple to state. Let's say someone has already computed all the physical onshell amplitudes. Okay, you have them at your disposal because you computed them previously. You can literally multiply those set of color stripped amplitudes by a certain matrix, and it will give you the ns, nt, and nu. Now, here's the problem. There's many matrices you can multiply them by to get various ns, nts, and nus. There's like a whole class of them. Okay, so yeah, there exists concrete formulas for these n's. It's proven in all orders. It's just a known fact. But they're kind of useless to understand why it's happening because there's so much freedom in getting these CK preserving representations. And let me give you, at least in my mind, here's what I hope is happening. I gave you this toy model of the phi-4 theory, where it's in this obscure Z2 breaking basis, but you can arrange things so that it preserves the Z2. Okay. Now, that basis where a Z2 is preserved is not unique, right? You could take phi-4 theory and send phi equals to a function that's odd in phi, like send phi to some strictly odd function of phi, and then you'll preserve the Z2. There's an infinite class of theories, of field redefinitions of phi-4 theory that still preserve the Z2. So there's still freedom. You won't find a unique Z2 preserving basis. And that's what I want or think is going to happen for CK, which is that there's many different ways of picking out CK representations because there's going to be many Lagrangians that have it once we understand what's happening. Okay, so that's a desire and aspiration, I'm not saying that's a proof, but mechanistically, there just exist formulas for these numerators. Yeah, practically speaking, yeah.
I have one more question, and I'm really confusing that. So in your Yang-Mills gravity, Yang-Mills spherical gravity, that in gravity, then the NS curve became the new NS for the gravity amplitude. Is it true? Then it means that.
Sorry, I didn't catch that thing you said. You kind of cut out. Sorry.
So the Yang-Mills curve equal gravity, then the NS curve became the new NS for the gravity. Then it means that NS curve plus NT square plus NU square is also zero.
I'm sorry, I'm just not hearing the question.
So I mean, your Yang-Mills curve gravity, then the 4-point scattering for graviton is NS curve for over S, right? Plus T plus U. Then that NS curve became the new kind of the kinetic vector numerator for the gravity. Then it means that NS square plus NT square plus NU square should be the zero. It is
No.
Yeah,
No. So you can't keep doing this. So when you take this factorization in Yang-Mills where it's C and N plus T plus U equals 0, and N plus N is 0, C plus C is 0. When you square it, you don't get to take the new kinematic numerator and say it satisfies the Jacobi identity, right? That would be akin to taking Yang-Mills and saying C times N plus C times N plus C times N is 0. No one's claiming that. So if you like, this is another way of saying that if you try double copying gravity, like double copying again, you can't do it. Like there is no Jacobi identity for N squared. So I think you're asking, does NS squared plus NT squared plus NU squared equal 0? And I'm saying it does not equal 0.
But you said that the kinetic fact the everything is proven for any theory, right? Then
No. So the claim is not that. I don't know what you mean any theory. So the claim is like, this is Yang-Mills and there's like, these are specific theories that are for which they're true. You can't just take a random theory and do this. Yeah. So maybe I didn't make that clear enough. Like, I'm not claiming. Well, if the color goes to diff, you could do that to any theory actually. But at least for gauge theory and gravity, like those are, if you like, I don't know, they're not special either because we know they're the only theories of spin 1 and spin 2. So you might say every single theory of spin 1 double copies to every single theory of spin 2. But like, there's just no other theories to talk of in some sense. But yeah, the idea is that like, this is a prescription for a theory that initially starts with a color, like Yang-Mills. I should say, I didn't mention this. You can do this for variations of Yang-Mills like QCD. There's in one of the double copy reviews, there's a huge table of other double copies, including QCD and biogravity and all kinds of other things. But the statement is not that literally every theory has this property. Maybe I should have made that clear. You can't take completely arbitrary theory and do this. It works for some and not for others. And because we don't even know why that is true, is why we don't understand the double copy. Right? If I've actually understood the double copy, I'd be able to tell you like, that's why it clearly works for this and not for other things. I would tell you the prescription that we know is true, but we don't have an actual deep understanding of why it would fail if you made up other rules and tried them. So I think you're pointing out, I think a good point, which is that like, take a random theory with like even weirder color structure or no color. How come I can't double copy that? I don't know, because I don't know why the actual original double copy is actually true from a real QFT point of view. But the hope is that once we understand it, then we'll be able to tell you, like, Yeah, that's why it works here and doesn't work here.
Thank you very much for the credit.
Well, thank you very much for all the nice lectures for the last 2 days. So we have a question and answer session in the afternoon after lunch. Why don't we move on? Cliff, would you be able to attend the Q&A session in the afternoon in our Korean time? It will be, I think, 9:30 in your time.
Yeah, I can attempt to make that. There's like a chance you'll hear the screams of children possibly running around. That's okay.
Yeah.
Yeah, if you're okay with just hearing screams, then I will try to do it. I'll send an email if I'll just try to show up. Yeah, it would be fun. I think maybe there's more questions. I'm happy to keep talking. I'm not sure about the day after, but I can try to make it tonight.
That'll be great. Thank you very much. Why don't we thank Professor Cheung one more time? Thank you.